Everybody, welcome back. We're going to work on another example for the sampling distribution of a sample mean. So let's look at this question here. We're asked, what is the probability that 5 people have an average IQ score? Hang on one second. It seems like you maybe weren't able to see that. Okay, yeah, hopefully you can see it now. You should be able to. So what's the probability that 5 people have an average IQ score of 111 or greater? And then we're also asked, how do the mean and standard deviation of the sampling distribution differ from the mean and the standard deviation of our population? So this is part D of this problem. Let me scroll up. So we're given here, right, that a data set of IQ scores are normally distributed with this mean 110 and a standard deviation of 10. So let me come down here to part D. Oops. Let's try that again. All right. So we're given, right, that our data set of IQ scores are normally distributed. Our data set, or maybe a population, make it a little more clear here, of IQ scores are normally distributed with a mean of 110 and a standard deviation of 10. So what's the probability that 5 people from this population have an average IQ score of 111 or greater? So let's start with that piece of our problem. Let's draw out our distribution. This is the distribution of our sample means, right? We've got, the question is asking, what's the probability that 5 people, right? So a sample of 5 people have an average IQ score of 111 or greater, right? We're not being asked the probability for one person having a single IQ score, right, of this or greater. If that were the case, we could just directly use our population distribution, but we're asked about a sample having an average, right? So we need to talk about the sampling distribution of sample means or sample averages, right? So our sample size from the problem is equal to 5. The average, the total average of all of our sample means, right? If we could take a sample of 5 people over and over and over again from this normal distribution with a mean of 110, right? A population mean of 110, then the average of all of those individual sample averages would be 110, right? It'd get closer and closer to 110, and if we could really take all of them, right, all the possible samples from this population, the average of all of the samples possible would be exactly 110. Okay, so we know that our mean of our sample means, right, is 110. So that means it'll be at the center of our distribution of sample means, right? Because we know from the central limit theorem that the distribution of the sample means is normally distributed, right? And a normal distribution has its mean at the center. Now we need to find the standard deviation of our sample means, right? We're given that the population standard deviation from our starting population is equal to 10. And if you recall, the standard deviation of our sample means is equal to that population standard deviation that we are sampling from, and we just have to divide it by the square root of our sample size. So we can take that population standard deviation that we're given and just divide it by the square root of 5. So looks like the square root of 5 is about 2.236. So if we divide 10 by 2.236, right? Square root of 5 is that 2.236, and it has got some change on it, right? But doing this division, I get about 4.47. So that's our standard deviation, right? So if we go one standard deviation up, 110 plus 4.47 is equal to 114.47, right? Going another standard deviation, we just add another 4.47. We get 118.94. Then if we go 3 standard deviations to the right, we just have to add one more. Whoops. 4.47. And we get 123.41. Now going down a standard deviation, we start from our mean, right, of 110, and we just subtract one standard deviation. So we subtract 4.47, and I get 105.53. We go one more standard deviation to the left, we subtract another 4.47, and we get 101.06. 101.06, and then if we go 3 standard deviations to the right, subtract another 4.47, and I get 96.59. So this is again, the distribution of all the sample means of size 5 that we could possibly take from this starting population that we were given. So we want to know the probability that a sample of 5 people have an average IQ score of 111 or greater. So if these are all of our possible sample means, right, we take a line, we have to find 111, right, which is somewhere around here, a little bit above 110, below 114.47, a little closer to 110, right, is our 111. And because we want the probability of having that average IQ score of 111 or greater, we want the area under the curve to the right of that 111, right? All of the numbers to the right of 111 on our distribution are all greater than it, right? So how can we find this probability? Well, we know we can use our calculator, right, with our statistics that we've come up with. So if I go to Google, pull up my calculator here, you should be able to see this. We can go to our second vars, right? We can hit option number 2 for the normal CDF. So our lower value, right, is that 111, right? That's the very smallest value we want. We want to know the probability of getting something greater than that. So in our upper, what do we need to put? We need to put 1 second, the comma button to get that E, the 99, right? That's how our calculator interprets positive infinity. So again, because we're looking for everything greater than 111, right? 111 is our lower cutoff. Everything to the right, all the way to the positive infinity, is our upper cutoff. The mean of our sample means, right, is the same as our starting population mean, which is 110. And we calculated that sample, the standard deviation of the sample means, right? It was different than our starting population standard deviation, right? We calculated the standard deviation of our sample means to be 4.47. So we can enter this all in our calculator, hit enter again, and we see that the probability of getting a average IQ score, right, of 111 or greater with a sample size of 5 is equal to 0.41149, 0.4115 we can call it, right, or 41.15%. And that would be our final answer down here. 41.15%, right? And now we're asked, how do the mean and standard deviation of the sampling distribution differ from the mean and standard deviation of our population? Well, we saw this, right? The mean of the sample means was equal to 110, and this was exactly equal to the mean of our population, right? Our population mean, remember, this mu is a population parameter, right? So here this represents just the starting population. This is the population mean or the population average of all of those sample means, right? So again, if we could take all of the sample means possible, then we'd have a population of sample means, right? So this is the population mean or average of all those individual sample means. And those things are equal. And what else did we see? We saw that the standard deviation of our sample means was equal to 4.47, and this was less than 10, which was equal to our population's standard deviation, right? So how do they differ? Well, the mean stays the same, but the standard deviation of our sample means actually gets smaller compared to the population that we start out with, right? And we've seen this in other videos. Based on the central limit theorem, right, our data becomes less spread out. It becomes more normal when we take the sample mean over and over again, right, according to the central limit theorem.